I said there's nothing really new to this lesson outside of the notation, the idea that we can take the derivative of the derivative. If there's a place where maybe I'm lying just a little bit, it would be how we do this with implicit differentiation. And it's not so much that there's something new, it's just something that you need to make sure you're aware of that's going to happen. So let's consider the circle. I think this is the same function we used when we first learned implicit differentiation. X squared plus y squared equals 25. Again, that's a circle centered at the origin with radius of 5. I want to find the second derivative of y with respect to x squared, and I'm going to evaluate it at the point 3, 4, which is definitely a point that exists on this particular circle. So again, even though I'm going to have to do this implicitly, I can't get to the second derivative without taking the first. So let's differentiate with respect to x both sides of x squared plus y squared equals 25. So I'm going to take the derivative of both sides with respect to x. We know here that this is going to be the derivative of x squared, which is 2x. And when I take the derivative of y squared with respect to x, that is going to be 2y, the derivative of y squared with respect to y, times dy dx. And then the derivative with respect to x of any constant is equal to 0. So now I need to solve for dy dx. If I subtract 2x, I get 2y dy dx equals negative 2x. And then I can divide by 2y and get dy dx is equal to negative x over y. So now I've got the derivative. I've got negative x over y. So the question becomes, okay, well, how do we find the second derivative? Well, I'm going to have to take the derivative of this right here. So I can say if dy dx equals negative x over y, then the second derivative of y with respect to x squared is equal to the derivative with respect to x of negative x over y. So I'm going to have to now apply the quotient rule to take the derivative of this particular expression. One other thing I'm going to do, I'm going to take the negative and remove it out because I can do that with any constant multiple. So this equals negative. Now when I apply the quotient rule, it's going to be the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. All right, so let's do this process and see what we get. We get y, well, let's start with the negative. Y times the derivative of x with respect to x is just 1, so that's going to be y. And then up here I get minus x. Well, the derivative of y with respect to x is exactly that. It's dy dx, and it's all over y squared. And you might look at this and think, hey, we got it. We executed the quotient rule. I don't have anywhere else where I need to take the derivative. The issue is you want your answer in terms of x's and y's because eventually I want to evaluate it at this point 3, 4. So the question is, what do we do with dy dx? Well, this is the part that is new, or it's maybe just pointing out that you can do this. You know what dy dx is? dy dx, we found it to start this. It's negative x over y. So I'm going to substitute it in, and then the rest becomes algebraic simplification. So this is going to be negative x over y squared. Okay, if I multiply this out, first of all, these negatives are going to cancel right there. So this is going to be y plus, and then I'm going to get a fraction in the numerator. So that's going to be x squared over y squared. If I want to simplify it, what I can do is I can also put y over y, basically finding a common denominator here in the numerator. This is equal to negative y squared over y plus x squared over y all over y squared. And now if I take a look at what I've got here, because both of these are over y, they're being divided by y, that can actually go into the numerator, excuse me, into the denominator. So if I can start a new line of work here, the denominator now is going to be y cubed. I still have my negative out in front, and then I get y squared plus x squared. So there it is right there. There's the second derivative. Go ahead and apply the notation here since we've just been writing a long string of equal signs. The second derivative is negative y squared plus x squared over y cubed. There's actually another interesting kind of point of simplification we can do for this particular one, but if you don't see it, it's okay, because we're still going to come up with an answer where we evaluate at the 0.34. But we actually know what x squared plus y squared is. X squared plus y squared is equal to 25. We actually, to make lives easier on ourselves, can just go ahead and replace x squared plus y squared with 25. And so the second derivative is really negative 25 over y cubed. Okay, the question asked us now, so if the second derivative of y with respect to x squared is equal to negative 25 over y cubed, we now need to evaluate it at the 0.34. So the second derivative of y with respect to x squared evaluated at that 0.34 is equal to negative 25 over y is going to be replaced with 4 cubed, and 4 cubed is 64. So this ends up equaling negative 25 over 64. By the way, that's the same answer we would have gotten if we had not made this substitution right here for 25. We just would have had to have actually plugged in 3 and 4. We would have still got 25, but it was just kind of a shortcut for us. So that's the process of taking the second derivative. A lot of times when you take the second derivative implicitly, right here, when we took the derivative of y with respect to x, we got dy dx. The biggest step to understand when you do this implicitly is you're going to have to make this substitution right here. You already found dy dx, so make sure it gets substituted in when you're taking higher order derivatives implicitly.